Modern man has become complacent about the vast and ever-increasing use of fossil fuels, whether for supplying power by burning or for conversion into manufacturing materials such as plastic. Yet one resource for manufacturing materials is still only used in very small quantities, and it is the lightest structural material known to man, magnesium. The astonishing fact is that we are literally surrounded by it. 2% of the Earth's crust is magnesium. There are incredibly vast quantities in our seas. Just 1 cubic meter of seawater contains up to 1.3 kilos of magnesium. And although the present global usage of magnesium is approximately 250,000 tons per year, the Earth's resources are so vast that even if we used 4 times that amount for 1,000,000 years, we would only use 1/100th of 1% of all the magnesium in our oceans. Magnesium is used for manufacture of components where weight and strength characteristics are of paramount importance, such as these highly stressed torpedo parts, or the wheels of this racing car. With special treatment, magnesium does not corrode, as demonstrated by this 100-atmosphere diving suit, which operates in hostile marine environments. Another example of magnesium's well-proven strength and durability is its use in the manufacture of components for the aerospace industry. Frank Kirk, a gifted design engineer with many years' experience in the automobile and aerospace industries, saw the possibilities of using recent advances in magnesium casting technology to overcome the problems encountered by the bicycle manufacturing industry in economically mass-producing a precision-built, lightweight frame. Frank Kirk's idea of a bicycle frame produced in magnesium, with all the desired performance characteristics of strength, stiffness, weight and response, was conceived with the aid of a very sophisticated computer, which produced mathematical models to analyze the criteria of production, stress, ride performance and styling in order to match the most sophisticated conventionally built frame. The manufacturing process itself would give the frame a consistent accuracy of alignment to a tolerance unachievable in a conventional high-volume production cycle frame, thus giving inspiration to the name Kirk Precision. The final design completed, the Kirk Precision frame now had to be proven in reality. Prototypes were built and tested by brittle lacquer and sophisticated strain gauge methods, and these tests proved that the computer model was remarkably accurate in predicting stress levels. Torsional stiffness tests were made by comparing a conventional race quality frame with the Kirk Precision, proving the Kirk to be 1.5 times stiffer. The measurements shown here are angular deflections of the head tube, measured after identical torque loadings were applied to both the conventional and the Kirk frame. This dynamic life test rig simulates full power loadings, exerting 250 pounds at the pedals. A dramatic difference can be seen in the torsional stiffness of the two frames. After this arduous test, equivalent to 100,000 miles of use, the frame's performance was unchanged. In addition to these rig tests, the Kirk frame was dynamically tested on a variety of road surfaces by Olympic standard racing cyclists. The results of these tests and the feelings of the riders confirmed that the Kirk Precision gave a highly responsive, comfortable ride, even under the most torturous conditions. frame being ridden here had already completed the equivalent of 100,000 miles of maximum power cycling on the dynamic loading test rig, and yet was still considered to give a performance better than a brand new conventional frame. To cope with the demand for the Kirk Precision frame, a new factory and production unit has been set up near London, England. With such a high-precision frame at such a low cost, the Kirk Precision is about to make a dramatic impact on the bicycle world.